Welcome. You likely know the parabola as the simple equation, y equals x squared. It is a staple of high school algebra, a smooth curve on a flat graph. But long before coordinates and formulas, the ancient Greeks defined it purely by geometry. They knew it as the specific shape you get when you slice a cone, parallel to its side. But here is the mystery. There is a second definition. A parabola is also defined as the set of all points that are equidistant from a single point, the focus, and a fixed line, the directrix. The question is, how are these two definitions related? How does a simple physical slice through a 3D cone magically create a curve with such perfect equidistant properties? To see the answer, we don't need complex calculus. We need a beautiful geometric insight from 1822, known as the Dandelin spheres. We fit a sphere inside the cone so that it perfectly touches, or is tangent to, three things: the cone itself, the cutting plane, and the generator lines. Where this sphere touches our cutting plane gives us our focus, point F. Where the sphere touches the cone, it forms a perfect circle, the contact circle. And if we extend the plane of that circle to intersect our cutting plane, we get our line, the directrix. Let's pick an arbitrary point, P, anywhere on our parabola curve. We need to prove that the distance from P to the focus is exactly equal to the distance from P to the directrix. Let's draw three lines. First, the distance to the focus, d1. Second, the distance along the cone's surface to the contact circle, d2. And third, the perpendicular distance to the directrix, d3. Here is the magic. Look at d1 and d2. Both are tangent lines drawn from the same external point P to the same sphere. By the tangent-secant theorem, often called the ice cream cone theorem, these two lengths must be identical. So, d1 equals d2. Now, look at d2 and d3. d2 travels along the cone's generator. d3 travels along the cutting plane. Because this is a parabola, our cutting plane is parallel to the cone's side. This means they share the exact same slope. Think of P as the peak of a tent. To get from P down to the bottom plane, you can slide down the cone, d2, or slide down the cutting plane, d3. Since both paths drop from the same height at the exact same steepness, the paths must be the same length. They form a perfect isosceles triangle in 3D space. Therefore, d2 equals d3. So, if distance 1 equals distance 2, and distance 2 equals distance 3, then logically, distance 1 must equal distance 3. The distance to the focus equals the distance to the directrix. We have successfully bridged the gap between the 3D conic slice and the 2D algebraic definition. This is the beauty of the Dandelin spheres. We started with a physical cone and a slice, and we arrived at the strict algebraic definition. It reminds us that algebra and geometry aren't separate worlds, they are just two different languages, describing the exact same truth.